Okay, and we're starting.
It's actually really fun.
Last time we looked at how to solve a system of equations with matrices, and we spoke about the convenient forms to get the augmented matrix in. Right now, let's talk about a few more definitions so we know about the language. And yeah, then we'll continue with that. So. That's what we saw last time. The actual system.
I had like the bean class. Well, I know a lot of people who didn't go to any of them. Since there's no pictures.
I lost the example for a second. It was 2x plus 3y equals minus 1, and x minus 2y equals 3. And what we did is we wrote this as an augmented matrix. Then we did a bunch of stuff, and we ended up at one final matrix that looked like this. We're going to see that form again today, and I believe it was 1 and minus 1. Right? 1 minus 3, 2 minus 3 is minus 1, and if I plug in 1 here, and then, yeah, so that's what we had. And we could pick out the solutions for x and y. So this was the solution for x. This was the solution for y. And this form of the matrix happens to be a very convenient form, which we refer to as the reduced row echelon form. And we defined what that was exactly and did a few examples where we identified when a matrix was in this form or not. I want to mention what actually happened here in the interim, all these kinds of things that we were doing. The steps taken here, the process has a name. It's called row reduction. Or we can say we perform row operations. And that's the first thing I actually want to define for you. So, row operations. These are mathematical operations. We can perform on a matrix that does not affect the solution of the system the matrix represents. Right? So we wanted to do a bunch of things, but we didn't actually want to change the answer to the original system. Everything that we did maintain the same answer, we just changed the matrix into a more convenient form where we could actually read the answer off exactly, right? Which is kind of what equations are all about in general, I guess. Like you have an equation and it looks very complicated, but you pretty much manipulate that equation in some way where all the equations are equivalent, and at the end you end up with x equals 5. So you go from an equation that looked complicated to one that's more simpler. We're doing the same process here with matrices, and we say we perform row operations. Now, each row in our augmented matrix represents an equation. So what we do with equations, we can do with the rows. And when it comes down to it, it turns out that there are only 3 legal moves that you can actually do. There are 3 elementary row operations. Now we're going to be doing row operations a lot in this section of the class. So you should know the kinds of things that you can do when you're trying to manipulate a matrix and know how to do them efficiently, which we'll talk about pretty soon. There are 3 types, only 3 legal things we can do. There is what we call the type 1. This is the operation that says we can interchange 2 rows. The equivalent of this was just writing this set of equations we had in a different order. If you just rewrite the order of the equations, it doesn't actually change the answer at all. So because you can rearrange the equations, you can rearrange the rows pretty much at will. You're not actually changing anything. Type 2. One thing we can do with an equation that will not affect how the solution is going to behave is we can multiply both sides of that equation by the same non-zero number. So, like if I have x equals 2, I can multiply both sides and say 2x equals 4. It doesn't change the fact that x is equal to 2. I just change the form of how the equation looks. I can multiply at any time by a non-zero number. Now, if I happen to multiply by 0, then that's no good because I only end up with 0 equals 0, and I've lost all the information. I've lost all the ability to actually solve for my variables. So I can't multiply by 0. I can multiply both sides of an equation by pretty much anything else, and this means I can multiply a row, I was thinking equations here, by a non-zero constant. The rows represents equations. The third thing I can do I'm going to state it in a funny way. It's not important for us to know it in this particular way, but there are contexts in which the particular way I'm describing it, it's very important that you follow it just that way. But that deals with determinants and a whole bunch of other stuff that I'm not going to talk about. But this is to replace a row by itself plus a multiple of another row. Right? Essentially for us, that was when we multiplied the one thing by another and added it to something in order to eliminate a certain place and to obtain a 0. But it's stated in this particular way because there are times when if you do it in the wrong order, it can lead to some consequences, but those consequences won't reach us, so you don't have to worry about it. That's just saying we can eliminate stuff by multiplying a row by a number to add it to something else to kill something that we don't want. And that's it. There are only 3 legal moves. At any given time when we're going through these operations, you have to be doing one of these 3 things, or a combination of some of these 3 things. It can do several of them at once in your head. But I wouldn't stretch that too far because it's very easy to make a mistake. But there are only 3 legal moves. Anything not listed here is illegal. If it's not here or a combination of here, it is illegal. It's very important that you know that. So, for example, if I have a row 1, 3, 7, 9, I cannot do something like you know what? I want to add 1 to everything. You get 2, 4, 8, 10. And here where you say, oh, this was row, let's say 2 plus 1. It turns out that would be illegal. You won't actually be able to do that. And why won't you be able to do that? Well, if you have an equation and you decided to add 1 to everything, you have now messed up the equation, because what's going to end up happening is you're adding 2 to one side and only 1 to the other side, right? So adding a number to a bunch of things just to get into a convenient situation is actually illegal, because you're actually messing things up, right? So pretty much any other mathematical thing you can think of doing to these things that's not one of those 3 things is wrong. And it's very important that you know that. So you can't just decide, oh, I'm going to subtract a number from everybody or add a number to everybody. It doesn't work. At any given time, you have to be interchanging rows, multiplying a row by a non-zero constant, or multiply one row by something to add to another row to eliminate something else. Everything else, illegal. That's very important. At any given time, you are doing one of 3 things. There is nothing else that you can do. Everything else is illegal. Okay. I'm repeating that for a reason. Okay. So, these are called the elementary row operations. It's pretty much the things that we can do with a row of a matrix that we can do with equations without messing anything up too badly. And let's do some more definitions before we move into the next phase. Matrices is still kind of new, so we want to make sure that we understand the landscape and the language. A zero matrix. I know it seems obvious, but there are contexts in which that isn't true. We'll never see such context though. So for us, zero matrix just means everybody in that matrix is 0. Notation, I might write 0 with an arrow over it, or 0 with an arrow m by n if I want to identify the size specifically. So I can think of the matrix 0, or the matrix 0, 0, 0, 0, or the matrix 0, 0, 0, 0, 0, 0. All of these are the zero matrix. There are multiple guys that can operate as the zero matrix depending on the size that you're looking at. Right? So this one in particular is the 0, which is a 2 by 3. And if for any reason I need to emphasize that, I would just write 0 with a 2 by 3 on it. So there are multiple guys that can act as zeros. And it would depend on the context. So that's why I call it a zero matrix, because there's no longer 1, 0. Matrices have many of them, infinitely many guys that are zeros. What else do I need to do? Definition. A diagonal matrix. Remember what a square matrix is? It just means the same number of rows are in columns. Is a square matrix in which any non-zero numbers appear on the main diagonal. Sometimes we omit the word main. If we just say the word diagonal, we did main diagonal. That's top left to bottom right. So, what are some examples of diagonal matrices? Well, pretty much any square zero matrix is automatically a diagonal matrix. So that's a diagonal matrix. That's a diagonal matrix. It's also that's a diagonal matrix. That's a diagonal matrix. Notice there's the diagonal running from the top left to bottom right. Basically, you would have a matrix where on that strip, any non-zero numbers show up here. Which means there are zeros literally everywhere else. Sometimes you might write just a big zero to emphasize that. So you have to write a bunch of different. Okay, so that should be understood. So this is called a diagonal matrix. Those guys are very important. I'm thinking of if we'll be doing anything where the diagonal matrix is going to be super important as a general idea. I don't think so. But there's one kind of diagonal matrix that's super important. It's called, D is the wrong word because again you can have several versions, but it's called the identity matrix. It's a diagonal matrix, so it's squared where all diagonal entries are 1, specifically the number 1. The notation, big I, or big I sub n if I want to particularly identify the size. So I1, for example, that's just that guy. I2 is the 2 by 2 diagonal matrix where there are only ones on the main diagonal. We saw this guy on the left of our system when we solved it last class. I3 would be a 3 by 3 with ones on the left and with ones on the main diagonal, zeros everywhere else. And so IN just means you have n ones and zeros everywhere else. That's just in general. So again, you can have multiple identity matrices. You can have one for each size. Now, why identity might be a question you might be asking. Well, it refers to multiplicative identity. Kind of like how 1 is the multiplicative identity for the real numbers, the I is the multiplicative identity, or some version of the I can be a multiplicative identity in the land of matrices. Namely, A n by n is a matrix, then if you take I times A, you will get I, as long as the I is the correct size. If you take A times I, you will get A. What size should this I be here? Huh?
Whatever.
It's like really bad. M or N, I can't really hear. This one here should be M, right? Because the inside numbers have to match up. And this one here would be N. So suppose I have A is the matrix 1, 2, 3, 1, minus 1, 0. And I wanted to find I2 times A and A times I3. Can run through the calculations for that very quickly. We're all experts at matrix multiplication at this point. Hopefully. So I2 times A is this. Take row times column. You're going to get 1 times 1 plus 0 times 1. Row times column, you're going to get 1 times 2 plus 0 times minus 1. Row times column, you're going to get 1 times 3 plus 0 times 0. Then you move on to the second row times column. 0 times 1 plus 1 times 1. Then 0 times 2 plus 1 times minus 1. Then 0 times 3 plus 1 times 0. You actually compute that. Here you're going to get a 1, here you're going to get a 2, here you're going to get a 3, here you're going to get a 1, here you'll get a minus 1, and here you'll get a 0. That's actually the original A. Something like that will always happen because the 1 is going to multiply the guy in the right corresponding component, and everyone else is going to get multiplied by 0. So it turns out something like this is always going to happen. If you went the other way, you'd realize that it will happen again. So if you take A times I3, that's going to look at 1, 2, 3, 1 minus 1 is 0. 1, 0, 0, 0, 0, 0, 0. Then you go through and you do the same thing. First row times first column. First row times second column. And first row times third column. Move down to the second row times the first column. And second row times second column. And second row times third column. And if you simplify that, you would again get 1 plus 0 plus 0, 0 plus 2 plus 0, 0 plus 0 plus 3, 1 plus 0 plus 0, 0 plus minus 1 plus 0, and 0 plus 0 plus 0. You're going to get A. And that's not a coincidence, it's always going to happen. Once your I matrix is the right size, if you multiply it by anything, it gives you the matrix that you multiplied by. It gives you the identity of the guy you multiplied by. So therefore it's called the identity matrix. Now, here are some remarks. For the same I to yield A times I equals A, and I times A equals A. A must be, what do you think? What can you tell me about A? I know it's very vague, but if I want to take this, it has to be the same, it must be squared, right? The number of rows and columns must be the same, right? So that way I can take the same I, say I3, and it'll work on either side because it's a square matrix, and it has to be squared. Which means non-square matrices won't have the same identity matrix on either side. Another thing that is worth mentioning here is that I want to actually compare to the real number system. One is the multiplicative identity. For R, right? So if I were to say, if I can take 1 times 2, and that will give me 2. I can also take 2 times 1, and that will give me 2, right? Now, there's the idea of a multiplicative inverse. Okay, so the inverse of 2 is 2 inverse. But by the laws of exponents, we actually know what that is. That's actually 1/2. Now, what is the property that this number has? If I take 2 and multiply by its inverse, what do I obtain? 1. This also works in the opposite order. If I take the inverse of 2 and multiply by 2, the answer is against 1, right? So the idea is, if we multiply a number by its inverse, the result is the identity. Right? And this is why division is actually a thing. We can actually define this to work for pretty much any number that's not 0 itself. On the real number system, every number that is not 0 actually has a unique number that this will work for. Right? Now, you might not have thought about that, right? So for 3, the inverse is 3 to the minus 1, which is 1/3. For 5, it's 5 to the minus 1. There's no other number other than 1/5 that will do this thing with the number 5, right? Now you might not have thought about that, but that property is why division exists. The fact that we can actually divide an equation and know what the answer is, and we can know that's the answer that results from division, is because of this property. Every number has an inverse, and it's unique. Once we can perform a division, which we can think of as a multiplication by the inverse, and we can always get the number 1, and that tells me that this guy is the unique guy that when I multiply by that guy, I get 1, right? Now, division is a thing because that works for every non-zero number in the real numbers. Does a similar idea hold for matrices? So oftentimes when we're studying new mathematical objects, we want to know how they behave in relation to familiar properties that we're used to. Because if they behave similarly, we can do the similar kind of tricks. So we want to know, does something like this work for matrices? If I give you a matrix, is there a unique matrix that I can multiply that guy by on either side and get an identity on the other side as the result? Now, the question is, of course, no right off the bat, because you've already restricted who this will work for, right? Only square matrices even have this possibility. Okay, and it's actually just a possibility. There are square matrices where this still won't work. Even then, there are problems. I can give you a few examples. Zero matrix. Is there a matrix that I can multiply that by on either side to create the 2 by 2 identity? And the answer is no. Okay. So if A is a 2 by 2, then if I take A times that 0, the result is going to be that 0, because I'm going to get 0 multiplying everybody, right? And if I take 0 times the A, the result is going to be 0. In particular, these are not the identities. So here's a square matrix, doesn't have an inverse. You cheated, Jhevon, you made zeros everywhere. Okay, let's not put zeros everywhere. What about this one? So this guy has no inverse. What about that guy? Maybe he has an inverse. Okay, so let's actually check it. Set A equals A, B, C, D. Then A times 1, 0, 0, 0 is going to look like A, B, C, D times 1, 0, 0, 0. If you multiply that out, you would get A, 0, C, 0. And that's definitely not going to be an identity because the identity needs a 1 in this position. So this has an inverse. You can talk about, well, you still put zeros in most places, Jhevon, so obviously that might be a problem because 0 we already know is a problem. That also has no inverse. Zeros are not everywhere. Everywhere I put a non-zero number. And you'll realize that if you were to play this kind of game and look at the results you get, you're going to realize that that thing could never actually be the identity. So even some square matrices don't have an identity. What is a consequence of this? Well, the consequence is simple. Have no inverse in the sense of the real numbers. And the consequences division does not exist for matrices. That is very important. Like there's a whole mathematical operation that is no longer valid for you to think about when you're talking about matrices. So if you like see a matrix equation, oh, A times B equals the matrix C, and you want to solve for the matrix B, oh, can I divide both sides by A? No, division isn't a thing anymore. Okay? So that'll work with numbers, it's not going to work with matrices. And again, on the surface when moving symbols around, it might feel like that's not a very intuitive thing to say, but because we know that matrices are really functions, this is actually totally makes sense. Because once you plug one function into another and you get some definition, there's no way that you can unorganize that definition in theory to get back the two original functions. You'll never really know what happened unless it was a very particular case, right? It's very hard to actually undo the composition, right? So for matrices, division isn't a thing. Okay? So if this is a matrix equation and you're like, okay, B must be C divided by A, I'm just going to give you a 0 and let this person has no idea what's going on. That is meaningless, right? The division isn't a thing and you can't do it. Not a thing, okay? However, the closest, we can get something close to division. And there is the concept of an inverse matrix, and not all matrices have them. You have to be square, and you have to be a special kind of square matrix to have one. So it's a very exclusive club of matrices that have this actual property. So let me actually tell you what the property is, definition. Let A, n by n be a matrix, so it's a square matrix. We say A is invertible. I'm defining that word. Or another word you'll see some textbook use, even though I won't really use it, non-singular. If there exists a matrix B n by n, so that the nice thing that works out with numbers actually works out with the matrices. If I take A times B, I would get the identity, and if I take B times A, I will get the identity. If such a matrix exists for the matrix A, I call A invertible, and that's just another way of saying it has an inverse. An inverse exists. We say A has an inverse, namely B, and we denote it by that. Of course, just to make it confusing, right? But it's very important that you realize this is not 1 divided by A. It's not like a law of exponents thing, it's a notation. So this is just what we call it. Not all matrices have these. We are going to, I'm not going to go really too much into inverses right away, but there's going to come a point where I'm going to tell you exactly how to actually find such a matrix when it exists, and how you'd even know that it would exist in the first place. Another thing I want to tell you about that is, we're not going to prove it, but it can be proven that if 1 works, so will 2, and vice versa. So you only need to check that one of these equations works if you ever need to do a check like this. So that's something else we need to learn about matrices now. Division isn't a thing. Multiplication is really function composition. And so that's why the definition is weird. Addition and scalar multiplication is pretty intuitive because with functions they're pretty intuitive. But division isn't a thing because if I can give you a random matrix and there's no guarantee you can find another matrix that will do this. Only the square matrices have those possibilities, but as I showed you with 3 examples, even some of them don't have a matrix that will do that. The ones that do, we call them the invertible or the non-singular matrices. Right? They're not single, they have someone that they can mingle with. So yeah, that is that. So this is always an equation that you can check to know if a matrix is invertible. If you can find another matrix that when you multiply it by it, you get identity, that tells you it's invertible. If you check it, the multiplication in either order, it's not going to matter. So that's important. Still going to wrap up with some definitions. We'll do some more math next time, but I want you to understand the landscape. What's allowed, what's not allowed, how do we call things. Yeah, so division, not a thing anymore. Okay? Not with matrices anymore. More definitions. You should know what the transpose of a matrix is. There's the idea of the transpose of a matrix, or A transpose. That just means you switch the rows and columns in a corresponding way. So the first row becomes the first column, the second row becomes the second column, etc. So example, A equals 1, 2, 3, 1 minus 1 is 0. Then if I turn the first row into the first column, so I just write that vertically instead of horizontally, second row into the second column, this is the transpose of A. And we have a notation for it. We'd call it A with the uppercase T in the top corner. That's the notation. And we sometimes call this A transpose. So if I remember talking in a minute, oh, A transpose, just transpose A and this is what I'm talking about. Switching the rows and the columns. That we should know. Trace, another thing that might come up. Trace of a matrix A. Now this one has to be square. It's the sum of the diagonal entries. So if A is equal to 1, 0, 1, minus 1, 2, 7, 0, 0, 4, then we call it the trace of A, that's the notation. That's going to be equal to, I'm going to add all the numbers that are on its diagonal. So it's going to be 1 plus 2 plus 4, or 7. Say the trace of this matrix is 7. So this is the trace of A. exposes traces. Explain the concept of the identity. We'll stop there.
For you, that's nuts. Like right now.
Yeah.
Oh my
I think we're done with definitions for a while. Now we're going to start like shooting a lot of stuff starting next class.
Oh, no, not yet.
I see.
Yeah, I think we can do also.